Today's problem, coin piles, difficulty medium. You are given an array of integers where each element represents the number of coins in a pile. You are also given an integer, k. Your task is to remove the minimum number of coins such that the absolute difference between the number of coins in any two updated piles is at most k. Note, you can also remove a pile by removing all the coins of that pile. Okay. So let's see. This is a better example here. The first example is not so good. What are the constraints here? The size of the array, 10 to the fifth. What is that? 100,000. The size of each pile is between 1 and 10,000. K is between 0 and 10,000. All right. Expected complexities. N log n. All right. Company tags. Microsoft apparently likes this question. Topic tags. Binary search, yes. Two-pointer algorithm. Are we going to do a two-pointer? Are we going to do a two-pointer algorithm with this? I guess in a way. Greedy. Not exactly the way I would think of it, but I don't know. You can decide. Those are possible topics here. N log n. So the binary search. We will employ a binary search. We'll go through each. We'll go through each element of the array. That'll be O of n. We are going to need to do a search, a binary search. So that's the log n. Let's take a look at what we're going to do first. The first part is pretty simple, and then I want to try to scroll this somewhere where we can see the code and maybe draw something at the same time. So we're going to sort the array. Well, actually, let's look at this example here first. What is the best way of doing this? Well, if we leave all the piles, if we don't remove any piles, the smallest pile is 1, and then we have k of 3. That means we can't have any pile with more coins than 4. Now we have two piles with 5 coins. If we took 1 coin off of each of those piles, we would be fine. And as it turns out, that is the solution. But how do we know that's the best solution? But we're going to sort this. We're going to create a prefix array. Prefix sum. Prefix array is just an array where you have the original array. The prefix array is a running total of the elements of the first array. And then what else? Okay, so here's the sort. Here is the construction of the prefix array. We're looking for a minimum value, so we're going to initialize it initially to a very large value. Previous, we don't use that right away. And at this point, if we scroll this down, yeah, we can't see the upper bound, but I'll tell you what the upper bound is. The upper bound, it's just a binary search, and I'll tell you what it's for as we go along. But okay, let's stop right there. Let me get a pen. And we'll use this example, 151251, but we're going to sort it. So it'll be 1 1 1 1 1 1 2 5 and 5. All right. We're also going to have a prefix array. So the prefix array, as I said, it's just a running sum. So it would be 1 plus 1 is 2, plus 1 is 3, plus 2 is 5, plus 5 is 10, plus 5 is 15. Okay, and actually let me put indexes here as well for the arrays. 0, 1, 2, 3, 4, 5. All right. The concept of this is very simple. We're going to take each number in turn. We're not going to repeat the numbers. I mean, the numbers are 1, 2, and 5, but we're going to take each number in turn and say, well, let's keep that as the smallest pile. Okay? So the first thing we would do is say, let's keep 1 as the smallest pile. Now, if we do that, that means we can't have any piles greater than 4. So these piles, the 1, 1, 1, those are fine. The 2 is fine. The 5s are not good. That would result in two coins being removed. All right, actually, let me make a note of that. 2. So that's our best so far. Let's say we're going to let 2 be the smallest pile. So now we can have piles up to 5 coins. But for 2 to be the smallest pile, we have to remove this, this, and this. That's what the prefix array is for, really, is to make it easier to see how many coins do we have to remove. We just go back 1 and say, all right, well, we have to remove 3 coins. The 2 and the 5, the pile with the 2 and the 5s, that's fine. But that takes 3 coins, and that's not better than what we have so far, which is 2 coins. And finally, we would say, well, what if we let 5 be the smallest pile? Then okay, then we have to remove the smaller piles, and again, we can look in the prefix array here and see that we would have to remove 5 coins. That is not better than 2. So 2 is the optimal answer there. But let's see how we can implement that as an algorithm. Okay, so let's try this. Here's our main loop. I is going to go from 0 to length of the array. If I is greater than 0, at this point I is not greater than 0. I is 0. For I equals 0, we don't care about previous. Previous is any smaller piles that we have to remove. Now, if we're at the first element, there are no smaller piles that need to be removed, so we don't care about that. Position equals upper bound. I'll tell you what the upper bound is. I think C++ has a built-in upper bound method, but what we want for the upper bound, we're going to send in the array. We're going to send in array at I, which in this case, I is 0. Array at I is 1. We're going to send in, array I plus k. 1 plus k, which is 3. 4. That's our target, 4. We can't have anything bigger than 4, and then we'll send in a low pointer, which is I, and a high pointer, which is the length of the array. And for the upper bound, what we want is the index of the first element of the array that exceeds array I plus k, that exceeds the target. Is too big. So in this case, we're going to call that upper bound, and we're going to get POS, position, is 4, because this 5 is the first element that is bigger than the key. All right, Total to remove. Again, first time through, previous, we don't care about previous. If position is less than n, which it is, the total to remove. All right, so how many are we going to remove? So we start out with prefix n minus 1. N minus 1 is the last element of the prefix array, 15. 15, that is the total number of coins that we have. We are going to subtract, let's see, prefix at position minus 1. Those all get to stay. We don't have to remove them. So prefix at position minus 1, that's here. So we'll go down here and 5. All 5 of these coins get to stay. So we got 15 minus 5. And then we are going to subtract n minus the position. N is the length of the array. Position is the first element that exceeds the key threshold. So that means in this case, it's pretty simple because it's a small array, but what it means is that everything from this point forward, from index 4 forward, is going to have to be reduced to 4. Because if we keep the 1s, we can't have anything in this array greater than 4. So what gets to stay is n minus the position. That's how many piles we have left here that are too big, and that is, in this case, 2. 2 times array at I, which is 1 plus k is 4, and 8. So 15 minus 5. These 5 get to stay. Minus 2 times 4. 8 of these 10 get to stay. So the total is 2. Okay? Because we initialized the answer to a very high number, total to remove is now going to be 2. Answer is going to be replaced by 2. So let me erase that computation. All right. But actually, let me make a note of it down here. This is our score to beat. Well, we already know that we're not going to beat it, but all right, we're gonna start incrementing here. I is going to go to 1, it's going to go to 2, but notice here that if an array element equals the previous array element, we don't care. We're not going to process it. So we don't care about these 1s. We've already processed 1. We've already assumed that the smallest pile is going to be 1. So we don't need to do anything with those. So I is going to go 1, 2. The only thing we care about is if I goes to 3, right? Now, is I greater than 0? Yes. If I is greater than 0, then previous equals prefix of I minus 1. So the prefix array at I minus 1, which is 2, that is 3. So previous is going to be 3. That means we got to remove the smaller piles. So, all right, position equals upper bound. Array I is 2 plus k is 5. We're going to do a binary search for that, and what we're going to find is that, in fact, the index that is greater than array plus I, 2 plus 3, which is 5, it's going to come in at 6, because none of these indexes is greater than array plus I. So it's actually going to come in at 6. All right, so let's change that. 6. Total to remove is previous is 3, so let's do the computation. It's 3, and then if position is less than n, which it isn't, n is 6, and this is 6, so the total to remove is 3, and that is too big. It doesn't beat the current number of, I think some of that just got chopped off, but to summarize, if we go with 2 as the smallest, total to remove, previous is 3, position less than or equal to n, it is not, it's 6, which is equal to n, so total to remove is 3. That doesn't beat the current best of 2. All right. I is going to be incremented again. I is now 4. All right. If I is greater than 0, which it is array at I equal to array I minus 1? No. Is greater than 0. So previous equals prefix at I minus 1. So the prefix array at I minus 1, which is 3, is 5. And so we're going to set previous to 5. Okay. Same thing is going to happen here. We're going to go for an upper bound. The upper bound is what index is the first index containing an element greater than array at I plus k. Now array at I is 5, and so array at I plus k is 8. There is nothing in here that's greater than 8. So again, position is going to come back at 6. Position less than n, no. So total to remove is just the previous, which is 5. And again, that is not better than what we already had, which is 2. Okay. Let's get rid of the writing here and try and run this. All right, I'm going to scoot this over so we can see the results. And let's go. All right. Don't I get a geek bit or something for that? I thought I usually do. Oh well. Anyway, so that's it. I'm still trying to think about the 2-pointer. Is it a 2-pointer solution? I don't know. Greedy. It might be greedy in the sense that we sort it and try to keep the smallest pile first. But anyway, that is the coins. What is it called? Coin piles. The coin piles problem. All right. Please like the video. Subscribe. If you subscribe, you'll get a notification in your inbox every time I post one of these, which should be on weekdays. And see you next time.